Well, thank you, Emil, for this nice introduction. So, again, my name is Johannes, and I will guide you through the first part of this presentation of Project Cyan. To give you a short overview of what we will be doing in the next hour, I will take you through an introduction to this topic, more from a bird's eye perspective. So we will not go too much into detail, as Emil just said. We will be keeping it close to the ISM notes, and I will be guiding you step by step how to generalize concepts that you have already seen in the internet seminar lectures, going from the Hilbert space via LP to, well, hopefully we will arrive at the Banach spaces, what we have in mind. And after the introduction, it's going to be the general Banach space setting, and at the end, some concluding remarks. So, in the beginning, let's make some standing assumptions. So we steadily assume that L is always an operator going from its domain to a Banach space X, which is assumed to be sectorial with angle phi L, just like in the lectures. It is assumed to be injective, and it has dense domain and dense range. And assuming that this X is not just a Banach space, but already a Hilbert space, we get exactly the theorem that you should all be familiar with right now. So this is McIntosh's theorem, taken straight from the lecture notes. There, theorem 8.4, relating basically the notion of quadratic estimates and bounded H-infinity calculus. And in order to give these concepts some sense, I will be writing down the notation which will be used throughout this whole presentation. All right? So at first, we have, of course, the bounded H-infinity calculus, which is always stated as f of L. Operator norm is up to a constant less than the subnorm of f on the particular sector. And here in the lecture notes, we talk about some angle or any angle. Those are equivalent in the Hilbert space case. So that's why this holds for f in H-infinity on the sector, and for some or any angle between the sectoriality angle of this operator and pi. Then B, which is not yet given, but I will be stating it anyway. This is going to be called a bilinear estimate. Okay, so we have already seen also that by now. So we take the inner product of f applied to TL, this whole thing applied to U, test it with V, take the modulus of that, integrate it against dt over t, and this is up to a constant less than the norm of U multiplied by the norm of V. For some, respectively all, f in H0 infinity and angles. Well, we have seen that perhaps bilinear embedding estimate is not the best name we could give to this condition here. And since nothing's being embedded right now, and also if you think back of the lecture notes from lecture 12, there was an exercise which basically referred to this notation. And there, such inequality was called a weak square function estimate. We also don't call it that because I don't see any square involved, to be honest. So that's why we will be referring to this as just a bilinear estimate. All right? So, and the last one, which is going to be C. This is the square function estimate that we all know, like the integral over the positive real line, norm of FTL applied to U, squared, integrated against dt over t, root that, and this is, well, up to a constant. We do everything up to a constant, so we do not, well, not less than, but actually we want the upper and lower estimates. U. There we go. So, and with this notation in mind, we can actually go from this qualitative version of McIntosh's theorem to a quantitative version of this. So employing these three notations, including the bilinear estimates, we have on Hilbert spaces the equivalence of bounded H-infinity calculus, the bilinear estimate, and also the quadratic estimates, and for each of them also with any or all auxiliary functions and angles. And as a cool side note, it's worth to note that in Hilbert spaces we indeed have that the H-infinity angle coincides with the sectoriality angle. All right. So what we have here, because just to relate them, we have A implies B implies C and back. There we go. All right. So from there, we will take a quick look at the key tools that were employed in the proof of McIntosh's theorem that you've just seen now, also with the bilinear estimates. So going from A to B, from the bounded H-infinity calculus to the bilinear estimates, the unconditionality lemma is being used. So you start basically with this term here, and by decomposing the integration interval into dyadic intervals, summing all those and doing a change of variables, you basically arrive at this formulation that we have right here. And yeah, we wish that the bilinear estimate holds, so this inequality, we want to have this inequality. And if we employ this unconditionality lemma, this basically gives us just what we need by reducing this whole inequality to an estimate about the operator norm that you just see here, taking the sup first of all the aj's in modulus equal to 1. For the second implication, going from the bilinear estimate to the square functions, well, we will see that later. There's a randomization argument involved that I don't want to take away from the speakers after me, so you will see that later. And the implication going from C to A relies basically on this lemma 8.7, which is the equivalence of square functions. What that means in particular is you take two functions, f and g, from the class h0 infinity, well, at least g being non-zero, and then you see that the associated square function norms are actually equivalent, or we get this estimate, and by reversing the rows, you also get the other one. So, all right, let me give you an example. So we are trying to go from the Hilbert space to LP cases, right? At first. We want to go to Banach spaces, but LP is the, well, better generalization at the moment. So let's see what happens if we just naively try to replace the norms we have here occurring in our assertions, but having here not the Hilbert space in mind, but actually the LP space. Okay? So what happens then? Well, I brought you an example. We take the Laplacian on the LP space on the whole domain, P being in the reflexive range and f of z being our familiar auxiliary function square root of z times the exponential of minus z. And this leads, if we use our definitions, this leads to this function right here. All right, so we insert TL into f, use our functional calculus, and we get this particular function that looks actually like a square function in the end. So we could call this actually a square function with the LP norm inside of this integral, but there's a problem though. Norms inside the integral, the LP norm inside the integral, does not really work. Why not, you might ask? We know by Little-Put-Pelly theory for the minus Laplacian that we actually have an equivalence with the norm of u in the LP space, but with a different expression on the left-hand side. So we know which kind of equivalence holds, so we cannot just go to another. All right? The heuristics here is that, well, if you take the space L2 with values in LP, this is not the same as taking LP with values in L2, right? You cannot just do that. There is a good case there, p being 2. But other than that, might be somehow difficult, all right? So in fact, we may find with the heuristics I just explained that from the square function from the example with the LP norm inside of this integral is not comparable to the norm of u with this particular choices of p. So we get one direction, but not the other, depending on which side of 2 we are, all right? There is another example in the paper of Cowling-Douche, McIntosh, and Yagi, which basically also looks kind of like this. There is no way we can salvage this with the LP norm inside of this integral, not in dimension 1, not with the different auxiliary function, and well, we just don't get the boundedness that we need of this integral, the boundedness from above. So we do not naively generalize this, but in fact we are going to use this particular square function norm here. In either case, well, this is not equivalent to u because we know what is indeed equivalent to u. This is not a good candidate as a square function. We use the one with LP norms outside of the integral, where phi is to the left of the sectoriality angle and f is in our suitable function class that we all know. So what we can actually do now, need some light. Okay, thank you. So what we do now, we take a look at our statements I have on the blackboard. Changing the H-infinity calculus to the case of LP spaces is rather easy because nothing has to be done. There is no H, there is no X involved here. We can just leave this as it is at the moment. Also with the bilinear estimate, nothing really has to be done. Think of, in the Hilbert space case, you have here the inner product going to LP. Think of it as a dual pairing. Same goes for the norm, the LP norm of u and the LP prime norm of v, prime being the conjugated exponent. What has to be changed is obviously the square function. So we take away those guys and take just this norm outside. So this will be our square function. We could conjecture now that such a statement, such a circle, still holds for the LP case. It is not that obvious at the moment. There are some more conditions that need to be derived to get this to work, but the other speakers are going through that. So just take it as a conjecture right now, all right? So, all right, going from there. We do now do something different, okay? We generalized our concepts here to the case of an LP space. But there's still more generalization that can be done. It's basically, we can do everything in a continuous manner. You see always, here are integrals involved. And while formulas may seem more understandable in a continuous setting, it's actually easier to reason with them in the discrete setting. So we are going to embark on a journey to discrete world. And at first, in order to do that, we need to translate what it means to have the connection between continuous notations of square functions and bilinear estimates and their discrete analogs. That's why I compiled this lemma of those two facts. On the left-hand side, we have the continuous version of the square function, also the continuous version of the bilinear estimates. And on the right-hand side, we have their discrete counterparts. And actually what this lemma says, well, those two are equivalent. Respectively, the square function and the bilinear estimates, of course. And because the other ones, going from the top row to the bottom row, would in fact be McIntosh's theorem that we do not know by now. So let me give you some steps of proof. At first, we take a look at the bilinear estimates going to the up direction. So we take, as I said before, the bilinear estimate term, decompose this interval of integration into dyadic intervals, sum it, make the change of variables, soup that, and there you have exactly what we need to have. Note that in this particular direction, in contrast to all the others, as you may see later, there is no loss of angle involved here. Whenever we use translation arguments from continuous world to discrete world, we might lose some angle involved. This is the only direction this does not happen. Where it does happen, well, is this one. Okay? So going from the discrete notation of the bilinear estimate, we can average it over this joint and linearly scaling balls. What I mean by that is the following picture. So we have this here, a sector. One of those points is the T2 to the J. Then we take a ball here with alpha. And basically what this alpha does, the one right there, what this alpha does is controlling the size of those balls. And as alpha gets bigger and bigger, those balls get slower. Well, not slower, smaller, sorry. All right. And then what happens, we integrate over a ball at first, then we can estimate this, we integrate over the whole sector. If I take the union of all those balls, this is, well, less than the whole sector. So we have this estimate right here. We make a change of variables, go to polar coordinates, and this right here seems like the continuous version of our bilinear estimate, but actually there is this loss of angle involved here. All right? So actually, I was just told that there is also a loss of angle in the case p equals 2. That does not make the statement wrong, but also in the special case of L2, we might lose some angle there. And the same goes for square functions. We can generalize this equivalence of continuous and discrete square functions to the case of more general Banach spaces. There is another condition involved there, namely the Banach space having finite cotype. And in books, there is actually this loss of angle given in a quantitative manner. So one can actually quantify this loss of angle. So, all right. So here, we're going to supplement our notation here by some B prime and C prime. B prime being the bilinear estimate in a discrete fashion. So sup of t between 1 and 2. Sum j being an integer. Modulus f of t2 to the j l u v. And this is less or equal than norm of u times norm of v. Well, and C prime being the discrete analog of our square function. So there we go. Norm, sum. Then we have, well, the modulus inside, not the norm, as we just learned. So L u square, root that, and take the norm. Well, and this should be equivalent to the norm of u. So, all right. And what we can also do, not done yet, what we can also do is extend this diagram going from B to B prime and to C prime. So we see if we have square function estimates, respectively bilinear estimates, in the one realm, we also have it in the other. So, key message to be taken away, we do everything in discrete world because it's easier to calculate stuff there. Secondly, Well, as I just mentioned, we lose angle when translating between discrete and continuous concepts. Point 3, does it help with Banach spaces? We shall see. And with that, I give it to the next speaker.
Thank you. Yeah, so far we've seen how one might generalize Macintosh's theorem to LP spaces and how to adjust the statements. It's worth mentioning now that if you adjust the statements as we've done before, the proofs start to break down. But before then, we want to adjust the statements one final time because we promised to do Macintosh's theorem on general Banach spaces. And so far, point A is fine for general Banach spaces. It's just H-infinity, bounded H-infinity calculus. B prime is also completely fine in general Banach spaces, right? So U will just be a norm, U will just be an element of the Banach space X, and V will just be an element of the dual X star. Where we want to run into a problem, of course, is C prime. So there's no, this modulus makes absolutely no sense in a general Banach space. So the very first thing we want to do is describe, okay, what do we mean by square functions in a general Banach space? So as has appeared in multiple talks so far, the way to do it is introduce some Rademacher functions. So for us, we're going to be using complex Rademacher functions. In other words, a complex Rademacher sequence, just a sequence of independent random variables which are uniformly distributed along the unit circle in the complex plane. And so if you want a very explicit example of it, just take exponential functions. And actually something very similar to this came up in the proof of Macintosh's theorem during the ISM notes. There was one step where we take, with a slightly different scaling, these trigonometric functions, and we use it to expand some discrete square sum as a kind of double sum with a product of these functions. So with this, we're ready to define our new, more general square functions, which are going to be these Rademacher sums. And so now that we've defined these, we're in a position to state the final form of what we want to do of our condition that we're going to use in the proof, which is that these more general square functions, so U, FL, which are defined to be these things, so supremum t between 1 and 2, and n some positive integer. Sum over Rademacher functions f t to the 2jl u. And so the equivalent, and so the condition C prime is now that this thing is equivalent to just the original x norm of u. And so in the end, what we're going to show is, well, before I get to that, first of all, I've been calling these things square functions. I haven't actually justified, first of all, that they have anything to do with square functions. So we should do that first, which is that for LP spaces, these Rademacher sums that we just defined really are just equivalent to the discrete square functions we had up there before, when, which Johannes introduced. And to give a proof of that is very short if we know these Kahane-Hinchen inequalities. And just so we're all on the same page, I will do that proof now very quickly. Right, so the thing we want to estimate are these Rademacher sums. And we're assuming for the moment that we are back in LP. Well, by applying Carnot-Hintschen for the first time, these are kind of L1 Rademacher sums. We can take it to be LP, so we can put a P here and do that. And this thing is equivalent to the one we took. Now, if you write out this as an integral and write out the expectation, just applying Fubini gives you a different formula, which is now we can take the expectation inside, and now it's the expectation of a scalar function. LU. That. Well, now we can apply Carnot-Hintschen again to this scalar valued thing in the middle here. So this will be equivalent to, and what we're going to do now is get it looking a bit closer to a square function. Which is, we're going to actually take squareds now. Because now we actually have squareds again, it's looking a bit closer. Now, we're going to use a very important property of Rademacher functions, namely that they are independent and they have expectation 0. So if we just write this out as, so this is the expectation of, not that. There we go. Possibly. Just to save me a bit of writing, I'm going to start calling these uj just at the end. Uj. So if we just expand out this modulus squared as k epsilon j uj conjugate, and then I will want the square root still. Sorry, thank you. Okay. So yeah, we assumed all of our epsilon j's are independent. They have expectation 0, and so when you multiply all this out, the only thing you're left with is when j is equal to k. Then Rademacher variables all have modulus 1. And so if you multiply it by its conjugate, it's just 1. And so after taking the expectation, we get equality here, which is exactly j equals negative n to n. Not that. What we're left with are these uj's squared, square rooted, and then the LP null, which is exactly our original square functions for LP. So these Rademacher sums really are a good generalization of square functions to general Banach spaces. So at this point, I'm going to get on with the proof. Sorry, I keep changing my mind now. So I have the nice job of proving the easy implications, namely A, which is that our operator has bounded H infinity functional calculus, implies B prime, which is our discrete bilinear estimate. And then I'll show this implies C double prime, which is our generalized square function estimate. And then Himani has the most interesting and most difficult part, which is proving this square function estimate implies bounded H-infinity calculus. So with that, the first proof. Bounded H-infinity calculus implies this discrete bilinear estimate. So you could actually pretty much derive this proof straight from the notes. It really doesn't use any complicated techniques. It's just noticing, first of all, if we choose some constants in a slightly clever way, then instead of this sum over the modulus, we can take the modulus outside. And why do we want to do that? Well, then we can take the pairing so that all of the sums of these f of t2 to the j are in the first term, and just our linear functional v is in the second term. And so we get this equality here. Now what we end up doing is, if we just now take supremum over v in the unit ball of the dual of x, well, this gives us a norm estimate for some element of x. If we then take the supremum over u, we get bounds on the operator norm of some operators. And so doing that, what we've actually shown is that this bilinear estimate certainly implies and is in fact equivalent to, it follows that it's equivalent to these operator norms all being uniformly bounded. But now, so what we're assuming right now is that L has bounded H-infinity calculus. From the lecture notes, we have the unconditionality lemma, which is exactly that these things you can bound by the supremum of the modulus of Aj. Well, we're taking modulus of Aj equal to 1, and this bound ends up being independent of both n and t, which we're taking supremum over. So since this thing is our bilinear estimate in disguise, we're done. So that was the first implication. Now the second one, that bilinear estimate implies equivalence of the norm with the square function norm. I'm also going to assume one technical condition on the f we're choosing for our square function norm. Feel free to ignore that condition completely. I'm only using it because it gives a nice short proof. Actually, part of Himani's talk will be showing that square function norm with an additional assumption on L, all square function norms will be equivalent. So you don't really need this assumption, but for now we will have it. So as before, we're assuming bilinear estimates. We just saw that this is equivalent to all of these operator norm bounds. But now what happens if we look at, instead of the Aj, what happens if we look at operators associated to our square function norms? Well, the epsilon j's are Rademachers. They always have modulus equal to 1, and so we can definitely bound this expectation by this supremum. But now just plug u, if you plug u into here, then we get exactly our square function norm of u. And what we're saying with all of these are finite, well, that means if we plug u into here, we just get, it's bounded above by a constant times the norm of u. And so we have an upper quadratic estimate here. And if we just take, and this dual square function norm was just to find, basically put stars on the operators. So taking the dual of an operator doesn't change the norm, so we get an upper square function, an upper quadratic estimate also for any functional v. So now what we're left with is showing a lower quadratic estimate, right? We want equivalence. We've shown the upper one, we want the lower one. So this is where my technical and not very necessary assumption comes in, which is we can use Calderon reproducing formula to write the duality pairing of some element u with v in this way. Now I claim, and I do have 5 minutes, so I'll be able to prove it, that if you take the modulus of this, you can bound it up by the product of these square function norms. So, as a quick proof. So the thing we're trying to estimate is modulus of this integral. So we saw in Johannes's talk that one good way of approaching this is split it up into dyadic intervals, use a change of variables. So that's what we're going to do, but we're also going to work with finite sums because it's slightly simpler. J. This now integral from 1 to 2, f t. And I'm going to move one copy of this f of t to the L over onto the dual side. Star v. Now, pull the sum and the modulus inside the integral and take out the supremum. And we end up getting supremum over n and t in this interval of, and I'm going to leave some gaps. Something Johannes said in the start of the talk is we're going to prove this part by randomization. So what we do is we just notice that, well, Rademacher variables are always modulus 1. So that doesn't change the value of the sum. If I do that and take the expectation. So now we've randomized it. So we can do the same trick down here, essentially going in the other direction, that if you have a double sum of two sums multiplied with Rademacher sequences, only the diagonal terms survive. So this is just about. Yeah, that's fine. Yeah. Two t to the j. L u t 2 to the j. Shit. Yeah, thank you. Yeah. Yes, do I? Yeah, taking the second. Oh, sorry, yes, good point. Yeah, that's better. Now, if you just use the standard inequality for the duality pairing and Cauchy-Schwarz, you end up with so the same supremum. Just about, yeah. Oh, I forgot it. That's what happened. Oh. Yes. Yeah. Just to save a bit of writing. But these things are precisely the L2 Rademacher sums. Use Kahane Kinchin again. These things are equivalent exactly to the square function norms. And so we have that estimate. Now we have that estimate, it's easy. So we've already proven the upper quadratic estimate on the dual. So use that. Then just take the supremum over the unit ball in the dual space. So the thing on the left just becomes the norm view. The thing on the right is bounded above by the square function norm view. And so we've shown the other half of the equivalence which we needed to show. And now for the hard part, I will hand over to Himani.
Oh, it was quick. I was thinking by the time the board will be cleaned, I could say something about a part here. But I hope you liked the first two part of the talk, which were creating a base for me. And I don't know, you can call me having an OCD or whatever. I just have an itch of writing it here. First of all, C double prime. And we have this f of L, the discrete square function, supremum over T in 1 to 2. Expectation, and you have summation. Why? Because, sorry about that. I just want to have a nice triangle here. We have a B prime, we have C double prime, and what Andrew has shown is this part and this part. Now it's my turn to do the reverse of it. Also, this is for the Banach space, and we also know the proof in the case of the LP spaces. All right, so coming back to my part of the talk, I would like to take you back to the, to the ISM notes. That is, I think, the easier to start with. You must have seen the square functions coming, and in the case of Hilbert spaces, and there was a lemma, that this is the lemma which shows the equivalence of two square functions in the case of Hilbert spaces. So, and there was a remark as well that says that you can take an extra function h in the h0 infinity class, you can insert an h of L operator, and then it can be still controlled by the h infinity norm of the function. So coming to the proof of this lemma here. So this was the proof in the internet seminar notes, of course, and we have this for the Hilbert space setting. Now, the idea for the proof was quite easy. If you see, we use the Calderon sibling, we write the relation using the Calderon reproducing formula here, and then the idea is to control the operator norm of this operator here by some estimate, and this is where the estimate played the role. Now, what we did here, we started with an L sectorial operator, and we use that for the case of L sectorial operator, we know that lambda r lambda L is bounded, and that is where we use that part and get to the case of zeta st. Now, so as it has been shown before, that we have an LP, the continuous case of the LP function here, the square function. I can't use the pointer here, but anyway, in this case, what you can try is, what if we just try to replace the square sums in the Hilbert space setting is replaced by the LP. So is the proof going to work similarly? Can we do exactly like that and get some estimates here? Now, the point is, as I said, that this brings you down to zeta st inverse. Now, from here to here, we use the boundedness of this operator. But when you have the modulus of this inside instead of the norm of that operator, this no longer works. So what do you do in that case? There is something that we need. So the additional information that we need is the R sectoriality. And this has been, we are seeing it from the very first day. What is R sectoriality? So I'm quickly going to go to the descriptions on the slide here by words. And this operator L is R sectorial for some angle phi. Then when the set here is R bounded. And in that case, the least admissible angle is denoted by phi RL as the angle of R sectoriality. All right. So now coming back to the discrete case, because that is what we have decided, we are going to work in the discrete setting and for the Banach space setting. So the lemma that I showed you before from the internet seminar notes is replaced by another lemma here that we have, is what I'm calling is a key lemma, because that is the lemma that gives you the H-infinity functional calculus from the square functions. So once you have the square function estimates, then you can get to the H-infinity calculus using this key lemma. So this is what we have in the case of the Banach space setting. Remember the norms that I have given is exactly here what I have written again. And this brought me down to the Macintoshian theorem on Banach space setting. And we have that L has a bounded H-infinity functional calculus. Then we come down to the point of having the bilinear estimates and then the square functions. Or rand, yeah, you can call this as the square sums here. And this is the Macintosh theorem that we have showed that A implies B implies C double prime is already shown. Now my task is to prove C double prime implies A prime, A. And the other point is this lemma, the proof for the case of the LP spaces in the continuous setting was actually given by Lemerdy. And in the case of the discrete setting and the Banach space, it's a result of Kalton-Kunstmann-Weiss, where instead of R sectoriality, they used a weaker condition. We can talk about it a little later. But so let me just show, once you have this lemma, how do we get to this theorem? I mean, how do we get to the part that my A C double prime implies A? All right, so what do we have there? We have norm of, so we want to show the H-infinity functional calculus. We start with any function H in H-infinity of S phi and consider norm of HL in the Banach space. Now, we see that in the square functions, we have the lower estimates. We can control this by, I would call it HLU with this norm here, the F of L, right? Now you can see that the lemma can be applied in this particular case. So I can use the lemma and show that this is the H-infinity norm and the, okay, it's some G, but I can take my F is equal to G because it works for all functions F and G. So here I bring it down to F, and then again we use the upper estimates of the square functions. And what we get here is the norm in the Banach space setting. So we have the H-infinity functional calculus for the operator. So once we have to show that the lemma, what we have written is actually proved, then this result will come out easily. So the idea is to prove this theorem, but before that, I'll just write the statement for the lemma quickly. And we have here H of L, U, F of L, and the norm is given here, is controlled by the H-infinity times the U of G of L. All right. Now, we can turn off the slide if possible, even the slide, so that I don't need it. The whole part is off board now, and I hope I should be able to write everything on the board. So let's aim to do that. I'll keep it as it is, but to prove the lemma, let's start with taking h is equal to 1. Maybe I'll start the proof on a separate board, and I'll keep adding the things once I have it in hand. So start with h is equal to 1. So what is this doing? Once we have h is equal to 1, so that our aim is to show that f of L is controlled by g of L for some functions f and g. In, say, you have, this is what we start with. All right, now, as you saw in the proof of the lemma that I just mentioned before from the internet seminar, we started with something called the Calderon sibling of a function g, and this is what is happening. So let's start. Let g hash be the Calderon sibling of g in the class h0 infinity as well. Then what you can do is integral 0 to infinity g hash t g of t dt over t is equal to 1. Also, by analytic continuation, so you pick any lambda in, so whatever angle I have taken so far is the angle phi, where phi belongs to phi L r comma pi, and I take something in between, say nu belonging to so what you can have by analytic continuation, that this is actually equal to t lambda gt lambda dt over t equal to 1. Okay. Now, so again, we have this statement, we have this, we can use the Calderon reproducing formula. And what does it give us? It gives us that you can have for an operator for, let's say, s is positive, then f of sl, u, for this particular element, we can have 0 to infinity f of sl g hash dl g of dl u dt over t equal to 1. Oh, sorry, what? Yeah, I'm sorry. Okay, you have this relation here. Now, what do we need? We have to get to the result that I have stated before, but look at this part. Thank you. Look at this part. What do we have here? F of SL, G hash DL. What can we do with this? Since we are working with the functional calculus, we can at least start with the Dunford functional calculus. So, FSL, G hash TL of U, apply the Dunford functional calculus on the angle that you have taken. Why did I start putting, my idea was to start with nu. This is why I was writing it. And on the boundary, Fs lambda, G hash T lambda, and then you have R lambda L, D lambda. Also, what you can do, you can plug in an additional lambda here divided by lambda. So we have some component here for this particular relation. Now, okay, let's define another operators. So let n lambda be integral 0 to infinity G hash T lambda G of TL dt over T, and m lambda is equal to lambda R lambda L n lambda. Now, one can notice that these two operators, n lambda and m lambdas, they are uniformly bounded operators. If you don't see it, you can ask that question, but I hope you can see it from the relations that's written. And jumping to the part where I'm actually going to use these operators is, okay, coming back to this point, f of SL. So we can plug this relation in this part here, and what do we get? 0 to infinity, 1 over 2 pi I f of S lambda, g hash t lambda, lambda r lambda L. But this is just the first part of it, and I keep the gt L u. I'll put the d lambda here, gt u dt over t. Now we apply the Fubini argument, and what we get here is okay, everything with does not have t, let's take everything outside. What do we left with is lambda r lambda L. Okay, we are here, and then 0 to infinity, we have g hash t lambda, then g t L u, then dt over t, and we have the integral in lambda here. All right, now what is this? This is my n lambda I started with. So let's put it here, plug it in. What do we get? fs lambda, lambda r lambda L. This is my n lambda u dt over d lambda over lambda. And what is this? This is my m lambda. I have here 1 over 2 pi fs lambda m lambda u d lambda over lambda. All right. Okay, so what can we do with this? We can somebody turn on the slides for me, because it will be back in some time, and how to bring the first one down? Okay, I just want to keep it till here, and let's see. I will write it, the discrete version of it, and what do? We do the change of variables here. You get f of r e I delta nu t m e I delta nu t dt over t. All right, let me call this as 1 over 2 pi I and some operator. Okay, not now. I am keeping this here and writing the remaining part of it here. To infinity, you can just take it. Did I miss anything here somewhere? Yeah, my s is gone. And other than that, it's all okay. Wait, what am I doing? Keep same variable. Yep. You can write this as r e to the power I delta nu m of s inverse r e to the power I delta nu d r over r applied on the function u. So let me call this as some k of s operator acting on u. Why have I done that? Till here, till here. I hope you can see the top lemma clearly. I don't know if everyone can see it. So there's a lemma that says that if k and m are two strongly measurable bounded functions and h is an L1 function, then what you can do is, and you can write the operator kt in this particular form, you can look at it like it's a convolution type operator, and what you get in the second part as a result of it is like a Young's inequality. And because the functions on the right and the left are actually like a square functions that we have already shown, then you can interpret it in that way. So what I have written here, KSU, and if I want to show you a little bit higher, what is happening here, we have the operator M here. This is the uniformly bounded operator that we have shown. The function f is in the h0 infinity class, and it comes in the h1 of L1 of r plus dt over t. Then you can consider this operator k of s as this operator here. Now, once you have this operator, what we can do, we can apply this lemma and come to the point of, okay, where?
Go on the front board such that you can lower.
Here? Okay, okay, let me bring it here. Because I started with h is equal to 1, I have written there. Let me start with this part, f of L, and this has gone down to the point of showing that this is the definition. I'm just rewriting maybe. Let's see if I have enough time to do that. But just to compare what is happening up in the lemma, it's better to actually have it written here. Now, for this particular function, because we controlled f of L u by calling its, doing the relation, it's under there, it's like with k of s operator. And this is what you can do here. We can use the lemma, and what we get an estimate is supremum over t in 1 to 2. Same here, expectation. And then what you get here is j equal to minus n to n epsilon j of m e to the power I delta nu t to the j u, and we also have supremum over the deltas with belonging in the set 1 and minus 1, yeah, whatever. And this is my n greater equal to 1. Okay, so what we have got here is this estimate from here, but we have the result that m lambda is equal to lambda r lambda L n lambda. So this operator we have shown that is r sectorial. We use the r sectoriality of this operator here, and we get the boundedness with this particular, we get an estimate with n. So let me get this n of e to the power nu t to the power j u in x. All right, now what? Now we have an operator n, but the form of the operator n is that it is the integral of g hash t lambda g of t l u dt over t. So how can we control this part? Now we have a result that says that, okay, I can actually plug the definition here exactly like this. Maybe, let me try to see. This, keep it summation. Okay, epsilon j, then integral g hash of t, all right, s t 2 to the j e to the power I delta nu g of sl u ds over s. And what we can do, since my function g hash is also an h infinity function, I can take out the h1, L1 norm of this function, and what we get here is supremum over t 1 to 2, the same estimate, n greater equal to 1. And since this will be taken out, what we are left with is So how are we doing that, by the way? How are we taking the G hash, the L1 norm of this outside? We are again applying the above lemma for assuming that my operator ms is now GSL, and the function h there is my G hash function. So we again do the same thing, and what we are left with is using that lemma, we get summation, some different here. There could be a change of variable that I could do. I should, instead of 2 to the power j, it goes here 2 to the power minus j, and then we get to the same point with just the expression here as it is, but it's all right. So we have epsilon k, some g of 2 to the power 2 to the power k t of L u x. Is that fine? So from here, what do we have? What is this equal to? This is what we have as the GL of the function u. This is what we started with somewhere here, and this is what we get here. All right, so this shows that the lemma is proved for the case when we take h is equal to 1. Now what happens when you want to do the general case of h? Since we don't have enough time, what I'm going to show is, all right. You can apply the R-boundedness of the Dunford calculus here, the way the R-boundedness of the set h of L, f of TL, and you can control the case for the operator h of L. I think I should show. You can show that f of L is controlled by the h infinity norm of this and the GL norm of the estimate that we wanted. So this will give you the proof of the lemma. Now there's a little bit part of the talk which is left and is covered by Andrew. So I hope so far you have enjoyed the talk and you continue to do so.
Yeah, so the final bullet point from the contents is concluding remarks. So first of all, one reason why we may be interested in this whole characterization theorem in the first place. Suppose you have some operator L where you know it has some bounded h infinity calculus, but possibly for quite a bad and quite a large angle. Well, if you can prove it's R sectorial, this bounded h infinity calculus for this angle gives you square function estimate. If you can prove it's R sectorial, then by Himani's lemma, you get square function estimates for all angles between the angle of R sectoriality up to the angle of R sectoriality. But square function estimates also imply bounded h infinity calculus. So we can get a better angle for our bounded h infinity calculus all the way up to this R sectoriality angle. Next, we've used R sectoriality. You don't need something that strong. You can do it with something slightly weaker called almost R sectoriality. That's done, for example, in the Kalton, Kunstmann, and Weiss paper. It requires just some slightly more technical manipulations. You can get some implications without any R sectoriality at all. So, for example, you can get, if you have a bilinear estimate for not a H0 infinity function, but a function in a more restrictive class, then Cowling, Daust, McIntosh, and Yagi show that that implies bounded h infinity calculus. And you can even get from square function to bounded h infinity calculus, but if you choose a very specific f. And one final thing, we've done everything for discrete square functions. There is a notion of continuous square functions using gamma Radonifying operators, and there is an entirely analogous theorem to the one we stated, but it's a lot more, going through that stuff is a lot more technical. So we didn't. And that's it.
So thanks a lot to Team Science. Ryan, for this very interesting presentation. We have time for a few questions and comments.
You showed at the beginning that in the case of LP you have this extra structure where you can derive something that genuinely looks like a square function norm. So is there a more general structure in which I can derive this norm, and how does it improve the results?
So you mean going from the norm here to the modulus and the norm outside?
Yeah.
Okay. Well, basically, I just know that through the Littlewood-Paley theory, the connection between this norm and this norm here on the right-hand side, that this holds. So that's why I just chose a particular example, which, if we were to carry this calculation out, then we would have actually seen that this norm equivalence here would not hold. Other than that, I'm not aware of any additional motivation that motivates the expression in LP.
Okay, other questions?
I'm not sure if my question was correctly understood.
Okay.
Ah,
Can I? No, so I meant what struct. Okay, so in the general Banach space, you explained that the expression doesn't even make sense. But so So if I have a Banach space that consists of functions, what additional properties would I need to have to recover the arguments that you did for LP in the concrete setting?
So there's two options. You can either embed your Banach space of functions into a Banach lattice, like embedding your Sobolev space in LP times LP, as many derivatives as you have. That's maybe not the lattice structure that you want, but then you can take absolute values. Or you have to go to, say, gamma redonifying operators or other types of Euclidean structures where you can then also build the whole theory.
other questions or comments? If there are none, then let's go to our well-deserved coffee break. And after that, there will be one more project.